Okay, we are recording. Okay, I'm going to share my screen. I have a few slides just to give a bit introduction so that for people watching the slide, watch the video knows the context. Okay, good evening, and depends on where you are, maybe good afternoon and good morning. So today is the webinar for the winners to share their solutions. I will give a brief introduction about the competition, and then I'll give that to Joe and Kristen from Meta to give the introduction about PyTorch, and then we will listen to the winners. So this is the PyTorch track for 2021 IEEE Low Power Computer Vision Challenge. So what is the problem? The problem is track multiple objects in video. As you can see, there are several people. These are Purdue students. They throw balls and catch balls. And the problem is we need to know who holds the ball. That's the problem. As you can see, some of them were wearing masks, so it was captured during the COVID time, and they get good outdoor exercise. The answer format will be something like the following. We will consider frame numbers. So if the balls, any of the ball change hands, then we want to know who holds the ball. So the ball may have different colors. Not all balls will show up in a particular video. Some balls have some videos have more balls, some videos have fewer balls, and some videos have more people, some videos have fewer people. But it will be something like the following. The solutions need to detect when a ball changes hand and then record who holds the ball right now. We also have some flexibility. We actually allow the frame number to be plus or minus 10. So if you are 1 or 2 frames before our simple solution, then that's fine. This is the top of the leaderboard. We can see many teams were busy submitting up until the last day. The competition was held from August 1st to the end of August, but because of time zone, so we actually allowed the last submission up to September 1st. And we can see the scores from different teams. We realized that the scores were pretty close, so we actually had another set of data that are not public, and we carefully checked whether the ranking has changed. So it's interesting that the ranking did not change, but the score have the gap between the scores have been much bigger. That's one of the reasons why we took us some time to decide the winners. Fortunately, there's no surprise. The ranking is the same, but the score with the additional data actually shows the bigger gap. The first award goes to the VITA team, and they will present their solution. The second award goes to the baseSlim team. The third award, the team decided to withdraw, and we also have an honorable mention, the spring team. I want to thank some of the key organizers from Purdue University, including Justin, Aiden, and Zitian. Thank you for your great work. We also, so they were reading 3 different sub-teams working on data collection, simple solution, and the referee system. Now I'm going to hand this to the Meta team to talk about PyTorch.
Thank you, Professor. Joe, if that's all right, I'll
go for
take it from you. Yeah,
sure.
So, yes, now in Meta and on PyTorch in particular, I think I want to reinstate like our excitement to look at the solutions that have been developed here and with these teams. Overall, I think PyTorch, is known for the research platform and framework that it is. And one thing that I want to reinstate also here is the importance that we see in on-device. There are trends happening out there with, for example, Facebook switching to Meta and how important it's going to make this field moving forward. But also we've seen with our community, the more research that has gone through on device because of a range of reasons from latency needs for the models or use cases happening, connectivity or lack thereof, and the need for a lot of AI to move on device for these reasons. Privacy also needs. And so what we're hoping to achieve with this competition and our engagement here is to keep learning more and more from the community and from these teams on what works for on device and how we can help support this better moving forward. So thank you everyone for your engagement. I know we're really excited to dig into these today. I'll let you take it back, Professor.
Okay, thank you. So how about we go from the, so I think we have two teams here presenting. How about we go from the second team, the baseSlim team from Meituan. You can present your solution, and then after your presentation, people can ask questions, including the first team. You are welcome to ask questions as well. And then we'll go to the first team and you can present your solution. So the baseSlim team is all yours.
Hello.
Yes, we can hear you.
Okay. Hello, everyone. My name is Yang Yong, and our team is from Meituan. And I will give a presentation of 2021 Low Power Computation Version Challenge. And this title is baseSlim towards extremely low power multi-object tracking with general compression toolkit. This is our content, and there are three parts: introduction of our solution, functions in baseSlim toolkits, and extremely low power pipeline with baseSlim. First of all, I will give a brief introduction of this challenge. Facebook is sponsor, and thank you very much. And hardware is Raspberry Pi 3B Plus, and software is PyTorch. We need to track multiple moving objects in video captured by an UAV, and the score is correctness divided by energy. The energy is measured by a power meter. Energy is the cumulative power of time. So so our solution is the multiple object tracking with general compressed toolkits. This is the flow chart of our solution. And the input data of video will be extracted one frame every 10 frames, and then will be the dynamic crop data. After that, it will go through a detection system. The output of the person detection will be re-identified, while the output of the board detection will be color recognized. The collision recognition will be executed at last. And so we used a deep source-like pipeline. It was mentioned that we didn't use fair mode because it is more suitable for one class detection and re-ID. So the deep sort is more flexible for this challenge. This is our detection part. We use the ULOX as our pipeline, and the training dataset is composed of Panda and sample data. There is no ball in the Panda dataset, so mosaic augmentation is good for the fusion of the datasets. And the input shape is 416. Because there is too there is too much redundant information in the frame of the video. We use the dynamic crop with the detection boxes from the last frame. We extract the main part of the picture so that we can get larger objects, which is good for the detection system. And this is our ready part. The output of person detection will be input into our ready model. Poison and the feature from the ready model will be considered in our match system, and the results of match system need to be corrected. So we add an ID recall model to recall the right ID from the ID pool. And this is our ID recall model, because the pool of the ID is enclosed scene in our video, in one video. So in other words, we can get the total number of the people in the input video through the ground truth at the beginning. So in this way, if ID number is more than the ground truth number, we can recall the true ID from the ID pool, and we update the ID pool after the matching system every frame. Now we introduce the parts of. Now we introduce the functions in baseSlim toolkits. There are 4 parts in our baseSlim toolkits. They are tensor quantization, filter pruning, knowledge distillation, and lightweight architecture. Firstly, we use the quantization with self-distillation. And the teacher model is the original network, and the student model is the fake quantized network. It is more robust to the long-tail distribution of features, and is much faster to convergence, even with biased samples. Then we use the hardware pruning, and we use the structure pruning for our challenge, for our solution. It is a more suitable method for a specific device. And besides, we use the serial and parallel group convolution in our backbone, which is proposed in SPGNet. It is an extremely lightweight structure for Raspberry Pi and is faster and better than FBNet with the same flops in detection and ready task. These are our submissions. The top of it is EuroX with baseSlim quantization, baseSlim pruning, and the re-ID with baseSlim quantization and pruning, and the lightweight structure. And all submitted solutions are optimized with QNPAC. Finally, we got the 8.556 score, which is the second place in this challenge. Thanks. That's all.
Thank you. Is there any questions from anyone?
Hi, Yang Yong. Thank you for your great talk. It's very interesting. I wonder, have you open sourced your baseSlim toolkit?
No, and that no, we don't we haven't open sourced our toolkits, but we will open source our solutions.
Another question is about the Panda dataset. Yeah. So
okay.
Is the Panda dataset is in the tracking literature? The Panda dataset. It should be the slide number 4, I guess. Number 4. Number 4. Yeah.
Okay. Okay.
Yes, this one. Panda. Is it from the tracking literature?
Tracking the teacher. What?
Oh, okay, I see. It's from the human-centric video data set. But how do you deal with the balls? I mean, if you use this Panda data set to be, I mean, the whole data set will be dominated by persons, and there'll be a severe problem of human label imbalance, right? So how you solve this problem in the training?
Okay, and the ball is not in the Panda dataset, but we have five videos from the sample data. There are many ball in them, so we mix the two datasets, and we use the mosaic augmentation to fuse the dataset. That's our solution.
Oh, I see. Oh, it's really smart of you to do that. Yeah, I don't even think of that. That's a really good idea. Very smart. Thank you. Thank you.
Panda dataset is from Tsinghua University, and it is a very large dataset, and it is videos by the camera, like the UAV. Okay.
It's a wide angle camera that is fixed, maybe on some buildings for surveillance. Oh, okay, surveillance camera.
Yes.
I see. That makes sense. Thank you.
Any other questions? Any question from?
I had a question.
PyTorch expert from Meta.
I have a question.
Facebook?
Can you hear me?
Yes. Go ahead,
so on one of the slides, I can't remember which one you mentioned. I think it was the one before this. You said it was very good on specific hardware. Does that mean that the pruning gets feedback from the performance on the hardware to optimize the layers based on the performance on that specific hardware?
My English is
okay.
Poor.
I'm sorry. I think it was here down one slide. Yeah, you said it is a more suitable method for a specific device. So
yes.
Does that mean you use like information about the device to do the pruning?
Yes.
What information do you use about the device?
So we have a Raspberry Pi, and we got the information of the speed of convolution layer, max pooling layer on the specific device, on the Raspberry Pi, so we can pruning. So the critical of the pruning is based the speed on the Raspberry Pi.
I see. And on one of the other slides, you showed pruning synapses and pruning neurons, I think. Did you use both of those techniques, or what did the pruned network look like?
What?
If you go 2 slides back.
2 slides.
Yeah, to slide 8. Can you go one more up? to slide number 8, where it says functions in baseSlim toolkits. Can you open that slide? Yeah, there. In the pruning section, it shows pruning synapses and pruning neurons. Did you do both of those?
No. We used the pruning neurons.
Okay.
Yes.
So the final model was still using like dense convolutions. You didn't have sparse.
Yes.
Okay.
We used the structure pruning.
Okay.
Yes.
Cool. All right. Those are my questions. Thank you.
Hi, I have a question. So I was a student leader of the drone video team, and I helped the development of the sample solution. And I wonder, how did our sample solution help you to like develop or improve your solution?
Okay.
Do you consider the simple solution at all? Do you look at the simple solution?
Yes. The simple solution, we change it, or we only change the detection model and the ready model. So the detection model is YOLO X, and the ready model is use our own backbone, and the coalition recognition, we change it a little coalition recognition, and it means which person hold which ball. For example, one person cannot hold the 2 balls at the same time. This point can this change can lead the 5 points at the last. Okay, that's all.
I have one other question. Did you measure power consumption and optimize power consumption, or did you try to go fast and you thought faster would mean less energy?
Fast. What?
Did you measure power consumption of your model, or did you only try to make it fast?
Fast.
Okay.
And there is a very interesting things which make our very fused, make us very fused. The PyTorch import touch this line, import touch this line can use the very long time. Very long time. I don't know why. Import touch this line.
Okay, that's good feedback for us. Thank you.
Yes, and this line on the Raspberry Pi used a longer time than our MacBook Pro.
Yeah.
Yes.
MacBook Pro is very powerful, very fast.
Yes.
Any other questions? Joe, do you have anything? Or Kristen, do you have anything to share?
Not for me, no. Thank you.
Chakri, do you have anything you want to discuss?
I don't have any questions. Thank you for the great presentation.
Okay. All right, so then let's thank you very much. Congratulations again for winning the second prize. So let's give the floor to the team that wins the first prize. Zhenyu, are you the speaker? All right. Start when you are ready.
Yeah, thank you, Purdue, for your hosting, and Facebook for your sponsorship. Also, Meituan and the other teams for your competing solutions, and your solutions as pushing us to the better ones, especially the last 10 days. So following the previous Facebook's members question, we actually use a USB power meter.
Sorry to interrupt. I think you are sharing a wrong screen.
Oh, my bad. Sorry, did I show? So silly. Sorry. I'm so sorry. So silly. Okay, are you able to see the screen? This one?
Yes.
Oh, okay.
Thank you.
Yeah, following the previous Facebook guys' question, so we built a USB power meter to measure the energy, and we found that the energy cost is linearly correlated with the latency. So basically, I would say on Raspberry Pi, to make the solution running faster is almost guaranteed to save the energy more. Yeah, okay. So let's start my presentation today. So we have members from UT Austin, Texas A&M, and Wormpex AI Research. So this outline, we'll first introduce the two basic tasks in the solution. They are detection and reunification. And then we'll introduce pruning and quantization for model compression. And later on, we'll introduce our solution for video action detection. And lastly, we'll introduce our proposed two modules to further save the energy. They are optimal pipelining and dynamic inference. This is two basic vision tasks used in this in our submission. So given the input, firstly we use the YOLO model to do the detection. It is able to give us a ball person detection bounding boxes, and then we would use ResNet 18 as a reunification models to obtain the identity labels for the persons and balls. And these two are the basic tasks, and these are the only two learning modules in our solution, and we all implement it using deep neural networks. So this summarizes the pipeline of deep association. So basically, given the input of detected bounding boxes of persons and balls, and we use this as a query. So we can see we have person queries and ball queries, and we use a ResNet 18 as an identity-aware feature extractor to extract the feature embeddings for the persons and balls, and we feed them into a gallery. So this gallery records the history of the person's previous feature embeddings, and we use this. Such a gallery stores feature vectors for both persons and balls, and we apply some matching strategies to make sure that the nearest neighbors are matched. And after the matching part is done, we are able to tag the identity labels for each persons and balls. In the model, especially for the pruning part, we tried two different strategies. The first one is knowledge-driven, and second one is data-driven. And we use knowledge-driven strategies to prune the YOLO model, because the YOLO model is very complicated, and we already have the prior knowledge that the three branches in YOLO v5, they are specialized for different for objects of different scales. For example, small, medium, and large. And we found that in this problem, ball persons, they all fall in the small scale. So we only retain the small scale branch and completely discard the remaining two branches, and saves us a lot of energy. And it also discards some ensemble blocks and replace some energy heavy modules with energy efficient modules. So this is we call them knowledge-driven model pruning. And the second one is we use some data-driven pruning to prune the ResNet 18 for person reunification feature extraction. And we further apply quantization-aware training to obtain a more efficient model. We know that neural network models, they are stored with float 32 or even first float 64 bit widths. So we reduce it to only 8 bit widths. They are unsigned integers. And this could save us a lot of both storage cost and the computation cost. The left one shows such a discretization, and in signal processing, it's called analog to digital, A2D. And the right one, it shows that how we simulate such a quantization behavior in the training, because directly doing the quantization after training would harm a lot of performance of the model. So we insert these kind of fake quantizations and fake fake quantization on the weight and on the activation to simulate the behavior. And such a quantization aware training would bring us very minimum performance loss in after the quantization. So Xin, your turn on the detection part.
Okay, thanks, Dr. Wu. Hello everyone, my name is Xin Hu, and this section will introduce the detection part for our model. And first, I want to introduce the training data set for our detection model. In this challenge, we choose a COCO data set as the training data set. And you know, there are many images in COCO data set, and most of the images are not suitable for this challenge. So we select some images from the COCO. The condition is first, a person and the ball must coexist in these images, and no additional objects are included in these images. Dr. Wu, could you click the screen? Okay. Okay, this is the selected COCO samples from the training data set. But there are several problems for the training data set, for the COCO data set. The first is a balanced level. The bottom figure is the level distribution for the COCO data set. And the number of person level is 22,000, and the ball is just 60,000. And there are also few occluded samples in the COCO data set. And the domain gap of the ball detection is larger in the COCO data set. To solve this problem, we did some data augmentation for COCO data set. Here we propose three COCO data sets. The left one is the detail for the proposed data sets, and the right is the example images for each data set. Okay, next. So with the synthetic data set and the COCO data set, we get the final level distribution for the new data set. And I think from the level distribution, the ratio of person to ball is 2 to 1, and there are multiple occluded samples in these images. And the domain gap of the ball detection is smaller than COCO data set. And we also did a texture shift best training for our training model, because we found our model trained with existing data set is strongly biased toward to texture. So we add some random shift patch with homogeneous texture in these training images. These patches serve as negative samples for ball detection. With this patch, our model is more robust. Okay, next. Here I want to talk about the design of our model. The first variant of our proposed model is a variant of YOLO 5. We retain the small object detection layer from YOLO 5, and we cut off one upsample block to change the small object detection layer to medium size object detection layer. And we decrease all channel numbers of convolution layers by half to reduce the flops. And all input images will be reset to 416 to reduce the flops. Next. We also proposed a second version of YOLO model. It's a variant of YOLO 3, and also we select the large object detection layer as the detection layer for our model. And we decrease the convolution thread in these downsample layers to change large object detection layer to medium size object detection layer. And also we introduce focus SPP and CSV model from Euro 5 to increase the accuracy for the proposed model. And we also change the convolution layer to depth-wise convolution layer in this model to reduce the parameters and flops. Also, we decrease the channel numbers of convolution layers by half, and the input images are reset to 416. Next, here are some experiments for the detection model. So first is the false comparison. The round marks are Euro 5 small, and the cross marks are proposed Euro Mobile V1, and the square is Euro Mobile V2. From figure, the Euro Mobile V1 with input size is 416. It reduced 16 times flops with just 24% loss on MAPC compared to Euro 5 small. And here is the energy comparison of different models. And all energy measurements are conducted on 60 samples by same Raspberry Pi and same parameter in 1 hour. And Euro Mobile V1 reduced 10 times the energy compared to Euro 5 small. And another interesting point is we found that the depth-wise convolution is not efficient in energy reduction for this situation because the square is the Euro Mobile V2. It uses the depth-wise convolution, but the cross mark is the Euro Mobile V1. It didn't use the depth-wise, but their energy are the same. So the depth-wise convolution is not efficient. Next. Here is the parameters comparison. Here I use 3 models to compare their parameters. And Euro Mobile V2 reduced 29 times the parameters compared to Euro 5 small. This means depth-wise could reduce the parameters, but is not efficient in energy reduction. That's the definition part. Hao-Yu, your turn.
Okay, hello everyone. My name is Hao-Yu Miao. I will be presenting the re-identification part of this talk. Following up the detection model, we need a way to identify each person detected by the detection model. And this is where we use re-identification. The goal is that given an input image, we want to be able to associate images of the same person taken from different parts of the video. So this slide describes the pipeline of re-ID structure. The first stage is sampling. In this stage, we will have 2 sets of image. The first set is the query set, which is the person image that we would like to identify. And the second set is the gallery set. This set contains images of every type of person. After the sample stage, the second stage is the feature extraction stage. In this stage, we have a pre-trained ResNet 18 model that we trained for identifying person. This ResNet 18 is like a feature extractor in which we input the image of a person, and the model will output the feature of the query image and the gallery image. So here, as you can see, we will have 1 feature vector for the query image and other 4 feature vectors for the gallery images. Once we have the features for each image, we then enter the last stage, which is the nearest neighbor matching stage. In this stage, we compute the distance between our query image and gallery images using cosine distance. This distance represents the similarity between different images. And so the image that has the smallest distance will have the same ID with our query image. And this is basically how we identify our query image. So this is the whole structure for the ResNet 18 model we used for the competition. We used the exact implementation from PyTorch. Basically, this model starts with a convolution layer with a kernel size of 7. and then followed by 4 basic blocks, and then an average pooling layer as well as a fully connected layer at the end. Next. And for the challenges we met for re-identification, in this contest, there are mainly 2 categories of challenges that lead to incorrect identification results. The first category is different camera view angles, and the second category is occlusion. Both of these factors can potentially make people change hugely on different frames, which makes the whole task more difficult. Here, I would like to specifically talk about occlusion. So under the occlusion category, there are roughly 2 factors. The first factor is ball person occlusion, and the second factor is occlusion between person and person. And not this slide, previous one, please. Previous one, sorry. Yes, as you can see in the picture, when a person is holding a ball, this causes occlusion that a ball may occlude any part of a person's body, which may potentially disturb how the model associates person. And the second factor is occlusion between person and person. This is very similar to ball occlusion, but instead it usually results in more occlusion compared to ball. And as a result, lower the accuracy of our model. Next. To solve this problem, our solution is occlusion-aware data augmentation. This is a simple data augmentation method where we try to add ball images and person images for occlusion in the training data during the training process. We add these balls and person images to make the model more robust to these occlusion factors. And we also expect the model to actually learn to ignore the occluded part and instead use the unoccluded part of the image when associating person. We have also tried other solutions such as random erasing data augmentation, and we found out that this method got more improvement for our scenario. Next.
Leo, I take it over till the end to make sure we can finish in the meantime. Yeah, thank you.
Sure.
So we tackle the second challenge, which is various camera view using a domain invariant feature learning. It can be treated as a minimax game. So here, FE, we given an input reality images and we feed it to a feature extractor. And it is followed by 2 classifiers. The first is identity classifier. This is a normal re-ID pipeline. And the right one will be the view classifier. It will classify what a camera view is a re-ID image is the input re-ID images. So we are able to get 2 loss, and these 2 losses plays in a minimax game. Basically, we would like to minimize the re-identification loss, and such a minimize. Let's look at this. Look at this equation. So the mean is applied on FE and FI, which is the feature extractor and the identity classifier. So it would like the identity loss to be small and the view loss to be large. So it would like to confuse the view classifier, and the max it plays on view. So it would like to minimize the view loss. So here we make them into a minimax game so that the learned features will be robust to different camera views, but it remains discriminative to the person re-identification. So this is our final result for model compression. So given the input ResNet 18, we first apply structure pruning on channels. It is able to give us 42 times flops reduction with only 21% MAP loss. And we fine-tune further fine-tune on the lower resolution images, because lower input or less pixels is guaranteed to give us less flops, and the less flops is guaranteed to give us less energy consumption. So such a way directly give us 4 times flops reduction with only 8% MAP loss. And we further apply a quantization of our training, and it is described in the below graph, and it gives us 3 times inference speed up with 3.7 times model size reduction and only 1% MAP loss. Such it is almost ignorable. And finally, it gave us a lightweight ResNet 18. I talked about the action detection module. So these are the 3 challenges in the action detection. The first would be the detection errors. It can be categorized into two parts. The first is miss detection. Such a missing detection would be resulted from the occlusions, and second would be false detections, or you can treat as false positive. So our learned model is still confused with those patches with homogeneous colors, and it confuses it, mistake it for balls. Although we have already tried the debias training, but such a problem still exists. And the second major challenge would be wrong association. It is resulted from the re-ID. For example, given an image, that person is occluded with another person, so our association would make mistakes. The third part would be because here we want minimum energy cost, so it's very hard to do the 3D scene reconstruction. It's very expensive. And because we cannot do 3D scene reconstruction, so reasoning the relations between persons and balls is very hard. So we propose a heuristic approach. So let's look at these symbols. The first, it means erosion or dilation, and the blue one means wrong association. The red one means misdetection, and those rectangles, it means collisions with different persons in different colors. We use different colors to represent the collision with different persons. So the first subfigure is a ball person collision history. The arrow is the time span. So we can see the ball. Here it only focuses on one ball because the moving trajectory for different balls, they are completely independent. So we focus only one ball, and such assumption is held in the challenge. And this, we can see that it has been collited with different persons, and this is a misdetection part, and this is wrong association part. We use red color to signify it, and this again is the wrong association. This is again the misdetection, and we first dilate it by theta slots, and this theta is a prior knowledge. So we use the half of the theta is the minimum flying time of the balls, and we carefully observe the sample videos, and we derive this from the sample videos. So we dilate it by theta slots, and my bad, should be theta over. Theta divided by 2. But anyway, we use such a dilation to connect these disconnected components. So after such a dilation, those unconnected components become connected, and we later on apply majority voting. Such a majority voting is able to overcome the association error and the misdetections errors. And later on, we erode it back, because we want accurate time to describe the catch time and the throw time. So such a action detection by erosion and dilation is able to give us a huge performance boost in the final score. And besides these modules, I mean, all the modules I described, they are proposed for better accuracy. So we propose other strategies to pursue lower energy cost. So this is the strategy we propose. It's called optimal pipelining. Here we trade the memory for less data movement. So let's make it clear. So here we have 2D models. They all have a lot of parameters, although we have reduced it to our best, but still a lot. And building the computation graph is even more memory costive and energy costive. And here, so we use some cache strategy to store the intermediate results, so that each model will be loaded only one time. And such a strategy is actually treating the memory, because we store all these images or crops, bounding boxes in the memory. Definitely it would cost more memory, but it gives us less data movement, and it means for the CPU, the cache hit rate, the real cache, I'm not talking about such as it's different from this cache. I mean, the real cache in the CPU, L1, L2, L3, those 3 levels of cache, the cache hit rate will be improved great. And such a trading strategy give us a lot of energy saving. So this is the overview. So given the input video, we store the image into the image queue at once, and we go to the ball person detection part. It gives us those detected crops, person ball crops together with the bounding boxes, store them into the crop cache, and we fed them into the deep association part. It is able to tag the identity labels for the persons and balls, and we store them into a box cache. The box cache only stores the bounding boxes and their identity labels, and we further fed it to the action detection. So it's just a plug-in and play. We use some cache strategies to improve the real CPU cache hit rate at the cost of more memory, not energy. It brings us energy saving. We further tried two different dynamic inference strategy. The first one is activity region selection. That's given for example, the input video frame at time t, and we already have its detection results at t-1, which is just a previous frame, and we have this detection results, so we are able to get its detection region initial guess. But we know that all person balls are moving, but because of the temporal coherence of the video, we know it won't move very abruptly. So we just add some residual region as delta x and delta y. So, and it will then crop the image out and feed it to the ball person detection. Such a dynamic inference by activity region selection give us again a lot of energy saving. And the last strategy we use is a collision inspection. Imagine we have a switch between the deep association and the detected bounding boxes and detected the persons and balls. So we just inspect whether there's any collision happens. Here we define collision as the center of the ball falls into the bounding box of the person. So if it falls into, then we say it's a collision. So we just inspect. If there's no such collision for any of the ball person pairs, we would say there's no, we don't need to run the deep association. It's just energy waste. So we just lift up the switch. But if there is collision, we would turn the switch on. We have open sourced our code at our VITA group, and if you're interested, you can visit them. And if you have any questions, just feel free to contact us. Yeah, that's all. So any questions?
I had one quick question. I mean, first off, thank you for such a comprehensive presentation. This is incredible.
Thank you. Appreciate it.
On the quantization, it's really cool that you guys use QAT. Oh, sorry, David, I jumped the line. Really quick, I guess I'm curious about your experience on QAT. Sounds like you got 3.7x speed up, and you reduced the model quite a bit. Did you jump right to QAT? Did you try static first? Like what was the process that you guys thought through and used to apply quantization? Oh yeah, really good question. We start with static or post-training quantization, static way. But it does not. The speed up is same as QAT, but the accuracy loss is large. Got it. Yeah. So later on we come to QAT, because QAT has such a quantization simulation and training, so the parameters is adaptive to the quantization, and it gives us minimum accuracy loss. Got it. Okay, that's really good feedback. Thank you. Cool. Thank you. Sorry, David, go for it.
I had a number of questions. No worry, I put my hand up after you started talking. Okay. Did you use the normal QAT in PyTorch, or did you have some other mechanism for quantizing? We use some third-party toolkit, like it's called the neural network intelligence. So, but they are calling your API, but they do more user-friendly wrapping on your APIs. Similar to probably what Lightning does, I think. Yeah, like that. They just do a better wrapper on your APIs, but the technology comes from you. Got it. Okay, my next question was, I saw you use on at least one of the two models a ResNet 18 backbone and then did pruning on it. I'm curious if you considered or if you tried other more recent architectures that are designed for mobile, like MobileNet, FBNet, EfficientNet, something like that. SqueezeNet. That's a really good suggestion. We plan to try it. We are actually writing a tech report to summarize our solution for the challenge.
So in the tech report, we will do a more comprehensive survey on different backbones. Definitely, we will try MobileNet and EfficientNet. They are definitely worth trying. But because of limited time, we only try ResNet.
Very cool. Well, it's awesome that you're able to get such great results, even with starting from a very old model. I guess the pruning was very effective.
Yeah, thank you for making the toolkit. Thank you for making toolkit. It's really useful.
Absolutely. Okay, I had a question about the ReID model that you said was pre-trained. Was that pre-trained on like ImageNet or something else?
ResNet? I don't think we do any pre-training because the ImageNet has a really large domain gap. The ReID data set, you can see the ReID data set, they are just person-centric. But ImageNet has 100 classes, 1,000 classes with all natural objects. It has a hierarchy tree ontology on it. So
right. I thought there was a slide that said that you used, at least you started from a pre-trained model, and I was curious about that.
Yeah, we may try, yeah, but we didn't use it. But I think you should be right. Maybe ImageNet pre-training gives a better initialization. We all know that the optimization for the model is very hard because it only use one first order optimization by SGD. But ImageNet pre-training would definitely give a good initialization point on the landscape, on the optimization landscape. Yeah, so I believe you may be right. We'll try in our tech report to see if ImageNet pre-training would lead to better performance for the ReID model.
Okay, my third question is actually about the slide that you have up right now with the person, the B there, the data aware augmentation with a person including another person. When you identify something like that, where you basically have a bounding box that has two people in it, how does the ReID model handle that?
Oh, that's a small question. I didn't mention in the. So we have two sources of the persons to be pasted. One is directly from the ReID data set. We have some pre-trained person segmentation model, but it is noisy. Some cases it would paste. It cannot segment the person perfectly. It have some noisy background, but still it works. This is one source of the pasted persons. The other source of pasted persons from Coco, because Coco.
Yeah, my question though is like, how does the ReID model respond when it sees a bounding box with two people in it? Like, how do you identify that person when there's really two people there?
It makes mistakes a lot.
Okay.
Especially when two persons are occluded very close, and made mistake. That is actually the second major sources of our action detection part, and such a ReID error will give the wrong association.
Got it. Yeah. And then my last question was, what loss did you use for training the ReID model? Was it like a, so how did you train it?
Triplet loss. We use triplet loss. We know
okay.
There are cross entropy loss, triplet loss, circular loss. We found that triplet loss is the best one.
And how did you get the labels for finding two pictures of the same person? Was it just labels from the training data, or did you also have something from Coco where you had identities?
Oh, those. I got a question. We didn't. The sample video, it's not involving training. It's fully for evaluation. We already have 3 ReID benchmark. They are Duke, MK, and the CUHK.
I see. So you had an external data set that let you use triplet loss for embeddings of the person images? Exactly.
We use 3 existing ReID benchmarks and we merge them together so that we get a large enough ReID data set to train the ReID model.
Cool. Well, this is very impressive work and I really appreciate the very detailed presentation.
Thank you very much. Thank you for your sponsorship.
Absolutely.
Hi. Yeah. Hi, Zhenyu. This is Xiao. Presentation. I found it very interesting, and I just have a few questions. So, if I understand it correctly, you actually have to go through the entire testing video first, and then so on the gap things that you mentioned later in the slides would work, right?
Yes.
So in other words, this is actually not a non-line method for tracking. So did you guys use any tracker to do the tracking, or you only use the detection and the re-identification?
Oh, good question. It's Actually, I read your sample solution a lot, and a lot of our ideas comes from your sample solution. But we didn't adopt your tracking idea because here we want minimum as small energy cost as possible. But tracking, in order to, if you want to do tracking correctly, it has to run on consecutive frames. And this is one reason. The second reason is here the UAV is flying. So in tracking there are a lot of SLAM SLAM strategies like Kalman filter. Those would no longer work because their assumption is constant moving objects or constant motion model. So we completely discard the tracking strategy and we only focus on association. So we don't do any prediction. We never try to track every body of person. So so that's our final adopted pipeline.
But apparently it worked very well. So still congrats. Yeah, amazing work. Yeah, thank you.
Yeah, I would owe at least 50% of our work to your sample solution. We inherited a lot of modules and used your a lot of ideas were inspired from you.
Yeah, thanks to the team. All right.
That's great to hear. Thank you.
Thank you.
Aiden, you might have a question?
Hello. I have 3 questions.
Yes.
The first one, how much time did you consume at the 9 import touch this 9?
In import touch?
Yes.
In
this 9.
Baseline?
Yes. How much time did you consume at this 9 on the Raspberry Pi?
Oh, how much time? I can't remember. I don't think we are the most efficient. I think one team they got more energy efficient model than us. Yeah, but I can't remember the exact number.
Okay. And the second question, how many frames did you skip?
Oh,
in your solution?
Oh yeah, we just use same as the threshold. If the threshold is 10, then we just skip 10 frames.
10.
Oh, 10. 10. 10.
Okay.
10. Yeah.
Okay.
The threshold in the judging criterion for the correctness.
Okay. And how did you skip your frame using OpenCV?
Oh, I know why you ask this question. Yes, I use OpenCV, and I know there are some other tools they can do better, but still at the time we don't know that. We use OpenCV, and we found that actually the bottleneck will be the video reading. Reading those ultra high resolution images is a major bottleneck. Yeah, maybe you have the same situation. Yeah, but I'm using OpenCV. How about you?
Okay.
Do you use OpenCV?
Yes, but I want to know. I want to know, how did you skip your frame? How did you skip your frame?
It's we read the video sequentially.
Did you use grab?
No, we didn't.
Grab?
We didn't use. We did some experiments. We found that will be even more time-consuming or energy consumptive. We cannot. We found an article, and they did some experiment. We also did some experiments offline. We found that reading the video sequentially is even faster than skipping. Directly read, set some frame, set some index and read the video. It's even faster than that.
Okay.
Yeah,
okay.
Sequential reading is the best way. Because I guess it would be the videos. It should be the video encoding part. The video, like the .avi or .mp4, they are all being compressed. So if you read it like in random order by skipping a lot of frames, it had to recompute a lot of things. But if you read it sequentially, because videos they have the property of temporal coherence. So that means neighboring frames, they are very close. So in the video compression part, you utilize such a prior knowledge, and when we decode it, if we skip a lot, then the computation pipeline or the decoding pipeline would be wrong for the OpenCV, and it takes a lot of time.
And I want to know, CV2 dot grab. This function, did you use it?
Grab. We didn't use this API, but I forgot which API you use. There are multiple APIs in OpenSea they can do, and they can select one frame from it. But we didn't use grab.
Okay, thank you.
Yeah, thank you.
Well, actually, I'm noticing this is the second year in a row that we've heard a lot about adjusting input resolutions and adjusting sampling rates in order to reduce energy consumption. And it occurs to me that that's something that you have to do when you're loading from a video. But if you were designing a UAV and designing the software and the hardware for that, that's something that you could just bake into the design. You wouldn't have to like pay extra to skip frames you don't want. So I wonder if next year we can do something to allow maybe some sort of config file that specifies what input resolution and frame rate the solution wants. And then we can sort of do that offline so they don't get charged the energy for that video transformation. And it might be less of a distraction for them.
Now we can check the video capture configuration and see whether we can do that. Anyone else has any questions? Didn't you have a question earlier, or Aiden? I thought you were raising your hand.
Oh, was there anything specific about the sample solution that you found to be pretty helpful?
And what else you would like to see in the sample solution to help you get a better understanding of what we're looking for?
Oh, yeah. I found that your data reading part, parsing, and the evaluation part, they are the most helpful. And also your initial pipeline based on deep sort is very helpful. We start from deep sort, and we just refine our idea on deep sort. Talking about what I expect more, yeah, I would say if you have the sample videos, maybe you can just annotate one video so that when we do the debugging, we debug on the 7P3B on that video. We manually label it, not every frame, but every 20 frame. I believe all the other participant teams, they have to do the label, because we at least need one video to do the validation or debugging. And in order to do the debugging, ground truth value is a must. So if you could, provide some ground truth, person ball labels on just one video, and maybe 50 frames, then be very helpful. That saves us the time.
Okay. Yeah. Thank you. That's a very good point.
Yeah. Thank you.
Notes. Yeah. Thank you.
I would like to notice there was some data in the data set provided. I don't know if you ever looked into that, but
yeah. We know there are some frames like exactly like this scene.
Yes.
I know in your release data set. Yeah. We use them. We did use them.
Okay, so you're saying like the entire video would have been more helpful.
Yes. We let me show you something. Okay, so are you able to see my Finder?
Yeah, yes. We can see it.
So I'll put this one. It's debugging. Single debugging. Yeah, this one. So we make a panel for debugging. So let me explain what this is for. It is divided into 4 panels. The upper left one is the predicted tracks, and the lower left will be the ground truth tracks, and the upper right would be the re-ID error. It displays the re-ID error, and the right one would be it displays the unmatched error. Just like if you given any tracks, they are unmatched, or any detection, they are unable to find a track to be matched. We displayed it. So we use such a debugging panel, and it shows the action detection results. Look at those wide font, wide numbers. It shows the action detection results. So we can see that it is able to tell us, so at what frame, what kind of error happens. For example, like this one. Yeah, like this. We found that this person number 5, track 5, is completely lost together with the red ball 13. And we found it's because the detection bounding box is wrong. I don't know why, but it detects the plain ground. So we are able to, we use such a debugging strategy to figure out what module makes a mistake, and we located the error and improve the responsible modules.
See, okay.
Yeah, but to make such a debugging strategy work, we need to have the ground truth tracks. So we manually annotate every 20 frames or every 50 frames. I can't remember. Yeah.
Okay.
Yes.
All right. Yeah. Thank you.
Thank you.
Yeah. Thank you.
Thank you. Congratulations again. Anyone else has any other questions or suggestions? Well, if not, then again, thank you and congratulations. We hope, Kristen, do you want to say anything?
Well, I just want to thank again all the teams that participated. I know we're learning a lot here each time from all of you. So thank you for the detailed presentation. I think there are some clear learnings for us also to take for next year, as David mentioned earlier. And so we hope to see you there in the next competition.
Yeah,
great. All right. Then
sorry to interrupt. I just have a last question. So Christian, are you interested in any summer interns? Because we do have some very strong team members. They are, they love Facebook, and their dream is to become an intern, to work for you in the summer. So do you have any position available?
I can pass along the intros to our engineering managers, and I think they'd be best suited there to see what's available. Yeah.
Well, that's great. That's great. Thank you very much. May I contact you offline?
Please do. Yeah.
Thank you. Appreciate that. Thank you so much.
Great.
Thank you.
All right. So I'm looking for possibly a conference or a journal for the teams to publish papers. I'm working on that, and when I have some progress, I will let you know.
Yes, thank you very much. Yeah, I'm very interested. And we can do some paper writing.
Thank you, and have a good day.
Yeah,
thank you.
I will share the recording and then with
Thank you.
Okay, bye.